In the last lecture, we focused on two continuous time processes, the Poisson process, which we've explicitly constructed, and pre-Brownian motion, which we constructed a la the Kolmogorov extension theorem in terms of its transition kernels. Now there's something special about the transition kernels of both of those processes. Let's look again. For the Poisson process, NT, its transition kernel, QST, is given by this formula here, which is the form we'll always get when we have independent increments. And this random variable, nt minus ns, is a Poisson distributed random variable with rate lambda times the Euclidean length of the time interval, t minus s. So that means that we can calculate this as the sum over all those integers in the set B of the Poisson probability mass function of the singleton m minus n. And the key feature I want to point out here is that therefore this kernel depends on s and t only through t minus s. We saw the same thing for our construction of a not necessarily continuous version of Brownian motion. There, the transition kernels were given like this, and the Brownian increment, bt minus bs, was distributed as a normal centered of variance t minus s. So once again, the dependence of the transition kernel on s and t is only through the difference, t minus s. Now what that means, in these examples and any others like them, is that the kernel, qst, will take the same value as q with the first time being 0 and the second being t minus s. After all, these two have the same difference between the two variables. So we're going to take that as a definition of a special kind of process which will soon become the primary kind of Markov process that we study. A collection of Markov transition kernels, or as Will stated, collection of Markov transition operators, is called time homogeneous if the dependence of q of s and t on s and t is merely through t minus s, which means that q of s and t is equal to q of 0 and t minus s, which we will henceforth denote just as q t minus s. In other words, we'll just index our kernels and our operators by a single time parameter, which is non-negative. In this case, the Chapman-Kolmogorov equations can be restated in a simpler form. They just say this, that q of s, q of t, is equal to q of s plus t, and q of 0 is the identity operator. Now that's exactly what Chapman-Kolmogorov says of these operators, but it also allows us to rederive the full Chapman-Kolmogorov in this time homogeneous setting. After all, if I have q of rs following q of st, if we have time homogeneity, that just means q of s minus r following q of t minus s. But with this property holding here, that's the same as q of s minus r plus t minus s. The s's cancel, and that just gives us q of t minus r, which is q of rt in the original notation. Now this is a very succinct and intuitive property. In fact, it has a nice name. If we have any family of operators on some space that satisfies this property, that it starts at the identity and q of s plus t is q of s times q of t, we call that family of operators a one-parameter semigroup. Now, if we have a Markov process xt whose transition operators are time homogeneous, then we call it a time homogeneous Markov process. And just to clarify, what that means is exactly this. For any bounded measurable function f on the state space, the conditional expectation of f at xt given f at s is exactly qt minus s applied to f, evaluated at xs. Perhaps it would be better to write this in the form the conditional expectation of f at x at s plus t given fs is qt f at xs. And that shows us something really nice about these processes. If we think of t as incrementing s, The process up to time s is here, and what this says is that if we get to time s and then increment by a small amount or a large amount t from there, then the conditional expectation of that back onto the new start time at time s only depends on the transition operators at time t. Now, this transition operator describes the distribution of the process at time t, given its starting distribution at time 0. And so putting these things together, we have this kind of heuristic, which says that the behavior of the process at time t plus s, given however it started at time 0, can be compared to what happens if we first let the process evolve, starting at that same initial distribution, until time s. We can tell everything about the finite dimensional distributions up to there, and then restart the process there. That is, we'll just call this a new process, x tilde 0, which starts at xs. Then we apply xt to that new process, and that gives us the process x tilde t, given x tilde at 0, which is xs. Now, in principle, those could be two different things. We let the process evolve for a certain time, stop it, start it where it stopped, and evolve to a new time, as opposed to just letting it evolve through from the beginning until the sum of those two times. What the Chapman-Kolmogorov equations say in the time homogeneous case is that these are equal, which is to say that you get the same process here if you stop and restart or not. Now, that is very similar to a property for linear differential equations, where this same kind of semigroup property describes their behavior. And that's not an accident. There is an important, fruitful connection between Markov processes and partial differential equations, which we'll explore a little bit later. But before we head in that direction, I want to make this heuristic a lot more precise. And this is where it's going to become clearer why it's useful to index the path space probability measure of the process by the initial distribution, not necessarily by the transition kernels, which we're thinking of fixed in the background. If we have a time homogeneous Markov process, then all of its finite dimensional distributions are determined by the initial distribution and the transition kernels. The initial distribution is just the law of the process at time 0. Let's recast our definitions a little bit, and instead of letting x denote a particular process with a particular starting time, let's let it denote the whole family of Markov processes with this fixed transition semigroup, where we're allowing the initial distribution to vary. In other words, we have a family of probability measures on path space, if you want to construct it that way. All of them have the same transition kernels, given by this semigroup of transition operators, but for each initial distribution, we get a different probability measure, and so this x denotes that whole family of Markov processes. Now, let's take any function f on paths. That is, it's a bounded function on the measurable space whose elements are paths, and the sigma field in question is the product sigma field. Typical examples of such functions f are, of course, functions of the process at some fixed finite number of times. That's how this sigma field is designed. Then we can, in principle, calculate all of these things here. That is, we take this function of our full process, and we take the expected value where we're specifying that the initial distribution of the process is nu. So instead of building that nu into the process here, we build it into which choice of expectation function we choose. That is, which measure here we're choosing, which is determined by the initial distribution. And to further confuse things a little more, in the special case where that initial distribution is actually a point measure, that is, we're saying let's start the process at a fixed point, not a random point, x in the state space, we denote this not as expectation delta x, but expectation just x. And the probability measure we call px. So with that notation in hand, here is a theorem which one might call the fundamental theorem of time homogeneous Markov processes. Given a time homogeneous Markov process x, which doesn't have a fixed start distribution but is rather a family indexed by all possible start distributions, and any measurable function on path space, then we can take the expected value of that function of the process with starting point x. That gives us a real number for each x. And that means we have a real valued function of x. That real valued function is actually a measurable function with respect to the sigma field B on the state space that we started with. And moreover, here's the important point. Given any initial distribution, if I take the process and shift it ahead time t, so that is, I take the new process which starts at time t. I start a process in some initial distribution, I let it flow forward to time t, and then I start the process there, conditioned on the sigma field up to time t. That will give me the same as the shifted process in that function conditioned on just xt. That is just a restatement of the Markov property, more or less, which we'll see in a moment. But critically, that same conditional expectation can be evaluated like this. We just take the regular non-conditional expectation of the function f at the whole process, but we start it at this random starting point, xt, where the process got to at time t. So let's make that a little bit clearer. If we take the regular expectation of this function of the process, starting at time 0, with initial distribution, a point mass at x, that gives us a function g at x, which in the first statement of the theorem is a measurable function. This means that we take that function of xt. So that's a very precise statement of this restarting property that I hinted at with the semigroup heuristic. If we let the process start at some initial distribution and let it flow until time t, then conditioned on the past up to time t, that shifted process is the same as the process starting at time 0, but not at the initial distribution, rather at the random point wherever that first one got to at time t. The process continually restarts itself at each time, starting from whatever point it got to and forgetting everything that happened before. Let's go ahead and prove this now. First, let's restate it in two parts. The first part, again, was that this function that takes any measurable function on paths of the whole process and takes its expectation with starting distribution, the point x, that function of x is a measurable function. And in fact, that statement there does not require time homogeneity. But the second statement does. The statement that no matter what your starting distribution is, if you shift the process forward t time units and condition on the past up to time t, that's the same thing as shifting forward and conditioning on where the process got exactly at time t, which is the same thing as just taking the unconditioned expectation of the function of the process at time 0, but with starting condition the random point xt where it got to at time t. Now let's be clear, I'm stating everything here in a way that probably sounds like it's intended for continuous time, but these statements hold for a discrete time set as well. In fact, they're easier to understand in that context, which we'll get to in the next lecture. So let's start, actually, by proving the first equality here. Actually, we've already done that, because this function of the process shifted by t units into the future is measurable with respect to the future sigma field past time t, essentially by definition of that future sigma field. Well, we showed in lecture 36.1 that if y is any bounded measurable function measurable with respect to the future of t sigma field for the process, then a restatement essentially of the Markov property for the process is that the conditional expectation of y given ft is the same as the conditional expectation of y given xt. So if we just apply that here with y equal to f at the process shifted by time t, we get this equality holding. So what we've left to prove is the second equality and statement 1, which is required to even make sense of the second equality. So for both of these, we're now going to restrict to a suggestively small class of functions of path space. That is, we're just going to say, suppose there is a fixed finite sequence of times, t0, which is usually 0, less than t1 up to tn, and that the function of the path just looks like some function of the path at time t0 times some function of the path at time t1, etc., up to some function of the path at time tn. And these functions should, of course, be bounded measurable functions of the state space. We're going to prove property 1 and the second equality in property 2 for these kinds of functions. And that proves the full result by Dynkin's multiplicative systems theorem. Since this class of functions is going to be a multiplicative system, and the statements that we want to prove here can all be formulated in terms of subspaces of all bounded measurable functions that are closed under bounded convergence. We have seen Dynkin's multiplicative systems theorem applied so many times now that I'm not going to make any attempt to write out the details of that later argument. It's just routine. So we will just say, once we prove that these things hold for this class of functions by Dynkin, they hold in general. So for property 1, the measurability claim, the expectation of that function of the process in starting distribution x, well, that just means this here. We're taking these functions of the process at those times. And now we know how to evaluate that in terms of the transition kernels. So that's just the integral of the initial distribution in the x0 variable, and then we integrate transition kernel from time 0 up to time 1 of x0 dx1, down the line all the way to transition kernel of tn minus 1 up to tn, variable xn minus 1 dxn, of this function f at x0 up to f at xn. And of course we can rewrite that as the expected value in the initial distribution point mass at x of this sort of alternating product thing, f0 times q of t0 t1 applied to fn minus 1 times q of tn minus 1 tn applied to fn. Well, taking the expectation with respect to a point mass at x is pretty easy. That's just f0 at x times this whole function here evaluated at x. Now, each of the transition operators is a function from bounded measurable functions to bounded measurable functions. And so I start with this bounded measurable function, I apply this transition operator, and I get a new bounded measurable function. Then I apply this transition operator, and I get a new bounded measurable function all the way down the line. So by induction, this is a bounded measurable function of x. And so this is a product of two bounded measurable functions of x, and is therefore a bounded measurable function, which proves the result in that case, again, not requiring any information about time homogeneity of the transition kernels. That's just always true. Now for property 2, once again restating it, we want the second equality here, which is the statement that if I start the process at time 0 in distribution near naught, and then I look at the process shifted forward by time t, conditioned on the process at time t, that gives me the same as if I start the process at time 0 at xt. And again, to be precise, what we're saying here is that if I define g of x to be the regular expectation of this function of the process starting at distribution point mass at x, as we just saw, that's going to be a measurable function of x, and the result is that this is equal to that function of xt. Well, again, we're doing this in the special case where our function is a tensor product of one variable functions of the process at a finite set of times. We're shifting the process t units into the future, and so this function of the shifted process is this product right here. We would like to compute this conditional expectation. Well, in order to do that, we're going to use the averaging property that defines conditional expectation. So we need to integrate this against any function that is measurable with respect to the sigma field generated by xt, which just means integrate it against some bounded measurable function of xt. We want to compute this for any such function h, which I've rewritten here in terms of the value of our specialized function. And now we're again going to use the expression for the finite dimensional distributions of a Markov process in terms of its transition operators or transition kernels. It'll be convenient here to insert a new function, which I'll just call 1 of x0. That is, we usually like to have the process at time 0 in the mix. Of course, we can do that just by taking that function of the process at time 0 to be the constant function 1. And then we can use our standard formula. This is the integral against the initial distribution at a variable. Since x0 is actually already in use, let's call this dx minus 1. And then we integrate q from time 0 up to time t, because that's the next time in the list, as we see here, of x minus 1 up to dx0, and then q from t up to t plus t1 of x0 dx1, and so on down the line, to q of t plus tn minus 1 up to t plus tn of xn minus 1 dxn, and then we have that function in there. We've got 1 of x minus 1, h of x naught, f naught of x naught, up to fn of xn. Now let's just note that by the time homogeneity, which we do need in this part of the problem, this q of 0 and t is just qt. This q of t and t plus t1 is just q of t1, and in general these terms are q of tn minus 1. Now let's look at the first two integrals here. We're integrating this new introduced variable because of this silly function here, but we're integrating out that x minus 1 variable here with this transition kernel times this measure. Of course, what that produces is just a new measure, and that measure is exactly the distribution of the process at time t, the law of xt. And so we can rewrite this integral with one fewer integrations. It's the integral of nu t dx naught, and then the rest of the things as before. qt1 x naught dx1 up to q tn minus 1 xn minus 1 dxn times our function h of x naught, f naught of x naught up to fn of xn. Well, let's just decide to combine the h out here with the initial distribution and leave everything else in place. So that gives us integral of h of x naught nu t of dx naught times everything else. And now what do we have here? Well, we've got this f naught of x naught here, which isn't being integrated out. What we're left with here after all those internal integrals is a function of x naught, and this is just multiplying that function of x naught. That's exactly what we saw in the last example. In fact, because what we have here is exactly the regular unconditioned expectation at starting initial distribution point mass at x naught of the function f naught at x naught, f1 at xt1, up to fn at xtn. That is to say, this whole part here is the expected value starting at the unknown point, x naught, of the function capital F at the process x. So altogether, what that shows is that this integral here can be written as the integral of this test function of x naught times this function of x naught, the expectation of the process starting at time 0, but with initial point being this variable x naught. And that's all integrated against the law of the process at time t. Well, If we combine those using the change of variables theorem, that says that this is the expected value with respect to the initial starting distribution we started with, mu naught, of h of xt expected value starting at xt of f at x. Of course, this is a function of xt by definition, so it is measurable with respect to the sigma field generated by xt, and therefore we found an xt measurable function which, when integrated against any xt measurable test function, produces this initial inner product that we wanted to compute by the averaging property definition of conditional expectation that shows exactly the property that we wanted to hold, concluding the proof here. So we've now seen a number of different precise ways to state the memoryless property of Markov processes. There's the original Markov property definition. There's a statement in terms of conditional independence of the past and the future, given the present. And now, in the time homogeneous framework, we have this new process restarts at every time statement of the Markov property. Everything we've done so far is fairly general and abstract, so next it's time to start looking at how these properties manifest themselves in some specific processes beyond the few that we've looked at. So in the next 2 lectures, we're going to look at some examples and some basic structural properties of continuous time and discrete time Markov processes.